Harness-R1, learning to edit executable runtime harnesses from agent failure trajectories. That is the paper on the chopping block today.
It's a huge one.
Yeah, it really is. And for the ML engineers and AI researchers tuning into this deep dive on AI paper slop, here is the core technical insight you need right up front.
No fluff, just the good stuff.
Exactly. So, when your LM agent fails during deployment, like maybe gets stuck in some endless loop or hallucinates a tool argument.
Which happens constantly, let's be real.
Right. And the standard reaction in the field is to either try to update the model's weights, which is expensive, or just sort of tape a new prompting strategy over the problem.
Yeah, just prompt engineer it away.
But this paper proposes a totally radical alternative. The researchers here, they post-trained a dedicated 9 billion parameter model that they call a harness engineer.
And they trained it using online reinforcement learning, specifically GRPO, which is super interesting.
Super interesting. But here is the kicker, this engineer model. It doesn't actually solve the tasks itself. Instead, it looks at the failure trajectories of a completely frozen target agent. And then it writes executable Python code patches to edit that target agent's runtime harness.
We're talking about dynamically modifying the environment context, the tool mediation, the recovery logic, all on the fly.
Yeah, and the critical piece of your training pipelines is that the engineer only receives a positive reward if its Python patch actually causes the frozen target agent to succeed on a rerun of that exact same task.
It completely reframes the deployment bottleneck. I mean, it really does. This 9 billion parameter model is beating massive frontier models at harness editing.
Which is wild to think about.
It is, but even more impressively, it generalizes to 20 unseen target models without any per-target retraining.
Which we'll definitely get into.
Yeah, we're looking at a framework that basically moves us away from static Python wrappers and points toward a future where AI systems programmatically code their own runtime environments, based on empirical failure data.
So, if you are building production agents, you definitely know the pain of watching a deployed model accumulate just massive interaction trajectories full of systematic failures.
Oh, yeah. The log reviews are painful.
Right. You look at your logs and you see the agent repeatedly misusing a specific API or losing track of its state in a long horizon task or just violating some strict JSON output protocol.
And the instinct is always to fix the core model.
Exactly. But why are the authors of this paper arguing we should focus on the runtime harness instead?
Well, because once a model is deployed, its behavior is largely fixed, unless you want to execute a costly weight update.
Which requires a massive data flywheel.
And serious compute. I mean, you can't just update weights every time a user finds an edge case. So the alternative most teams rely on is injecting static, fixed prompting rules, like self-refine.
Okay.
But the researchers point out a fundamental flaw there.
Right, because if we think about an LLM as like a race car engine, the runtime harness is the transmission, the steering column, and the pit crew.
That's a great analogy.
Thanks. I mean, you could drop two identical engines into two cars, and they will perform radically differently on the track if one has, like, a broken steering column or a pit crew that doesn't know how to change tires.
Exactly. The model weights is really only one piece of the performance puzzle.
Yeah, the harness dictates how that intelligence actually interfaces with the track. But I know plenty of ML folks who rely on self-refine to act as that pit crew. They prompt the model to reflect on its mistakes and try again. Did the authors test that standard approach?
They did. And the results are actually a pretty stark warning for anyone relying heavily on prompting hacks.
Oh, really?
Yeah, they found that fixed rules like self-refine actually lowered the average reward across the benchmarks in this paper.
Wait, lowered?
Lowered it by an average of 2.6 percentage points.
Wow. That is actively degrading the agent's performance. Why does a reflection prompt make things worse?
Because a fixed prompting strategy applies a one-size-fits-all heuristic to every single failure. It completely ignores the specific mechanical breakdown of the target agent on that specific task.
Oh, I see.
Like, if your agent is failing because of a really subtle syntax error in a SQL query, feeding it a generic, please reflect and refine your answer prompt often just confuses it further.
Right, it doesn't know what to reflect on.
Exactly. Or it causes it to hallucinate a completely new, incorrect approach. You need a surgical intervention tailored to the actual failure mechanism, not just a blanket instruction to, try harder.
Right. Try harder doesn't fix a broken SQL join.
Right.
So if generic rules fail, we need a way to programmatically intervene based on the specific failure.
Yeah.
How does Harness-R1 actually structure this intervention?
So it relies on a strict dual model architecture. On one side, you have your target agent. In the primary experiments, they use Quen 3.59b.
Okay, making sure I follow. This target agent is entirely frozen.
Right. Completely frozen. Its weights never update. It is out there executing tasks in the environment, making mistakes, and generating those failure trajectories.
Got it.
Then on the other side, you have the harness engineer. This is a separate trainable model, also initialized from Quen 3.59b.
So it's a 9B model fixing a 9B model.
Yep. The engineer receives a batch of these failure trajectories. It analyzes the exact sequence of observations and actions that led to the failure, and then it outputs a JSON patch.
And this JSON patch contains actual Python code.
Actual Python code.
Yeah.
Designed to prevent that specific error.
Okay, but if I am receiving a JSON patch containing Python code, I need to inject that into the target agent's execution loop. And an execution loop has multiple stages. Where exactly is this code going?
The architecture defines 4 strict lifecycle hooks where the executable patch can intervene.
4 hooks. Okay, lay them on me.
The first is episode initialization. This hook runs before the task even begins. So the Python patch here can modify the initial context, set up specific state variables, or retrieve particular skills the agent might need.
Okay, so that's the setup phase. Then once the episode is running, the agent has to process an observation and decide what to do. I imagine you would want a hook right there before the LLM generates its thought process.
Precisely. That is the second hook pre-decision. This allows the harness to inject state-conditioned hints into the prompt right before the model thinks.
Oh, that's highly dynamic.
Very. The Python code can evaluate the current environment state and generate a specific warning or reminder tailored to that exact moment in the trajectory.
Right, so then the model thinks and outputs an action. But before we send that action to a live API or a database, we need some sort of firewall.
Which brings us to the third hook, and arguably the most powerful one, pre-action.
The action mediation layer.
Exactly. It happens after the LLM has decided on an action, but before that action hits the environment. The Python code injected here can validate the action against the schema, rewrite it if it's slightly malformed, or just block it entirely and force the agent to reconsider.
That's super useful. And if the action does go through, but the environment returns a failure, like, say, a 404 error on a web page or a SQL execution error, you need a way to handle that without the agent just repeating the same bad action.
Which is a classic failure mode for LLMs.
Totally. They just spam the same broken API call.
Right. So that is the fourth and final hook post-feedback. This triggers recovery logic after the environment returns an observation.
So it catches the error.
Right. If the agent gets stuck in a loop, the Python code here can recognize the repetitive state and inject a hard interrupt, basically forcing the agent to backpedal or try a new tool.
Okay, so those 4 hooks provide total control over the execution lifecycle. But injecting arbitrary Python code generated by a 9 billion parameter model into a live runtime, that sounds like a security and stability nightmare.
Oh, absolutely.
If you manage production systems, your alarm bells are ringing right now.
Yeah.
What happens if the engineer model writes a syntax error, or worse, like an infinite loop?
The researchers definitely anticipated that, so they built a strict sandboxing and validation layer.
Okay, phew. How does that work?
Before any generated patch is even considered for execution, it is parsed offline. If the Python patch contains syntax errors, if it violates the JSON schema, or if it attempts to access forbidden global variables outside its designated scope, it is instantly rejected.
So invalid patches just have zero effect on the runtime.
Exactly. They are treated as a complete no-op, and during training, the engineer just receives a reward of 0 for that patch.
Okay, that makes sense. This sandbox ensures that only syntactically valid, safely scoped code ever touches the frozen target's runtime.
Yep, it keeps the blast radius contained.
A sandbox keeps it safe. But training a 9 billion parameter model to write highly specific, logically sound Python guardrails autonomously, that is a massive challenge.
It's notoriously difficult.
Usually, we rely on human senior developers to write that kind of middleware. How do you actually train the harness engineer to do this?
The training pipeline requires 2 distinct stages. You have your cold start supervised fine-tuning, or SFT, and that's followed by outcome-grounded group relative policy optimization, which is GRPO.
Okay, let's break those down. Start with SFT.
Right, so the SFT phase is really just about teaching the model the format and the basic syntax. They use a highly capable teacher model, GPT 5.5, to look at a set of failure packets and propose executable patches.
Okay. So they use a frontier model to bootstrap the 9B model?
Yes, but they do not just accept GPT 5.5's output blindly. They validate these teacher-generated patches by actually running them on the frozen target.
Oh, they test the teacher's homework.
Exactly. They filter out anything that fails or regresses the agent's performance, and that distillation process yields roughly 1,000 high-quality executable examples.
So they use those 1,000 examples to supervised fine-tune the Q9B engineer.
You got it.
But SFT alone is fundamentally limited. I mean, it teaches the model how to format a JSON and write a valid Python loop, but it doesn't teach it how to truly solve novel, complex runtime failures.
Exactly. It's just mimicry at that point.
Right. Which brings us to the GRPO phase. And for the ML practitioners listening, the way they structure this RL loop is honestly the most elegant part of the paper.
It really is beautiful.
Because in standard RLHF pipelines, you usually train a proxy reward model, or you use a massive LLM as a judge to evaluate the generated output. But Harness-R1 strips all of that away.
It bypasses the proxy entirely, which solves a massive problem in code generation.
Let's get into the mechanics of that.
Okay, so here is how the GRPO loop functions. For a given batch of failures, the harness engineer samples 8 different candidate patches.
8 distinct Python patches.
Right, and each valid patch is installed into the frozen target agent's runtime independently. Then, the target agent reruns the exact same tasks that it previously failed.
The exact same task.
The exact same ones. And the reward signal sent back to update the engineer's weights is simply the realized performance difference on those specific tasks.
This directly attacks the plausibility versus utility gap.
100%.
If you use an LLM as a judge, it might look at a Python patch and evaluate it based on syntax and logic. It might say, this code looks incredibly sophisticated, 10 out of 10.
Right, it looks plausible to a human reviewer.
But if you deploy that code and it doesn't actually fix the target agent's failure, it has zero utility. Harness-R1 only updates the engineer based on the empirical delta in task success.
Which is exactly why GRPO is perfectly suited for this, because it calculates the advantage token by token within that group of 8 sampled patches.
Okay, let's break down what that means mathematically for the optimization process, because that's super important.
Sure. So it uses a token-averaged clipped surrogate objective.
Right.
In standard PPO, you need a separate value model to estimate a baseline, right? And that adds immense computational overhead and instability.
It's notoriously a headache to tune.
Exactly. Well, GRPO group relative policy optimization eliminates that value model entirely. Instead, it normalizes the rewards across the group of the 8 candidate outputs.
Oh, so it's comparing the patches against each other.
Exactly. If one patch causes the agent to succeed where the others fail, that patch gets a positive relative advantage.
That is so clean.
It is. The algorithm then clips the probability ratio between the old policy and the new policy to prevent destructively large weight updates, and then it updates the engineer token by token based on that grounded relative advantage.
And during this entire gradient update, only the 9B engineer's weights are changing. The target agent remains completely frozen.
Right.
You are optimizing the pit crew while leaving the engine exactly as it is.
Yeah.
So the architecture is sound, and the objective function forces actual utility.
Yep.
But we really need to look at the empirical results here. Did this actually improve the target agent across rigorous benchmarks?
The baseline results are highly compelling. They evaluated the system using the vanilla Quinn 3.59B target across 3 heavily distinct environments.
Distinct environments are crucial. What were they?
First is WebShop, which tests grounded web navigation. The agent has to search for products, parse HTML layouts, and select specific options.
Okay, that's tricky. Lots of noise in HTML.
Yeah. Second is ALFWorld, which involves text-based embodied household tasks. So navigating through rooms, finding objects, manipulating them in a specific sequence.
Classic long horizon planning.
Yep. And third is DBBench, which tests strict SQL database querying and manipulation.
Where a single syntax error results in total failure.
Exactly. Very unforgiving.
That's a great mix. You've got semantic HTML parsing, long horizon physical planning, and strict code generation. How did the frozen agent perform before and after the harness intervention?
So across those 3 environments, the baseline vanilla Quinn model achieved an average success rate of 44.3%.
Okay, 44.3.
After the Harness-R1 engineer analyzed the failures and injected its Python patches, that success rate jumped to 53.6%.
Whoa, that is a plus 9.3 percentage point increase.
Derived entirely from dynamically editing the runtime harness.
That's massive. But, I mean, the obvious counter-argument from a well-funded AI lab would be, why bother training a 9B parameter engineer model when I can just use an API call to a 100 billion parameter frontier model to write my Python patches?
It's the logical question, and the researchers actually tested that exact scenario. And this is where the plausibility versus utility distinction becomes undeniable.
What did they find?
They prompted GLM 5.2, which is a massive frontier model, to act as the engineer using standard zero-shot prompting. It only achieved a 48.8% average success rate.
So the 9B model beat it by almost 5 points.
Yeah. Then they tried DeepSeek V4 Pro, which is renowned for its coding capabilities.
Oh, for sure.
It only managed to add a plus 1.0 point gain.
Ouch.
And incredibly, Gemini 3.5 Flash actually lowered the agent's success rate on ALFWorld.
Wait, we have to analyze why a state-of-the-art model like Gemini makes the agent perform worse than having no patch at all?
Right.
How does that happen?
It stems entirely from the lack of that RL rerun loop we talked about.
Do empirical grounding.
Yes. Frontier models are optimized during pre-training and standard RLHF to output text that looks structurally and logically sound to a human evaluator. So when you show them a failure trace, they easily diagnose the surface-level issue, and they write a patch that seems highly plausible. But because they're operating zero-shot, they have absolutely no mechanism for grounded trial and error.
They write the code and just hope it works.
Exactly. Consequently, they frequently write patches that are over-constrained. They introduce this rigid rule that fixes the isolated failure they observed, but that same rule accidentally shatters the agent's ability to solve 10 other tasks in the environment.
Oh, that's such a classic software engineering anti-pattern. Fixing one bug and causing 10 more.
Exactly. Without the same batch rerun loop providing an outcome-based reward, frontier models have no feedback mechanism to understand if their code genuinely improves the overall utility of the agent.
So a 9 billion parameter model trained on the harsh reality of execution vastly outperforms models hundreds of times its size that only optimize for code plausibility.
It's David versus Goliath, but David has a compiler.
I love that. But if I'm an ML team lead listening to this, my immediate concern is lock-in. Because ML teams swap out their underlying foundation models constantly, right? Llama drops a new model, everyone switches. If you train this harness engineer entirely on Qwen 3.59b's failures, doesn't it just overfit to Qwen's specific behavioral quirks?
That's a super valid concern. To answer that, the researchers conducted a massive cross-model transfer experiment.
Okay, good.
They took the fully trained Harness-R1 engineer, the one trained exclusively on the 9B Qwen model, and they applied it to 20 completely unseen target models. 20. We are talking about vastly different architectures and scales too, including Llama 3.1 Akin 0B, Gemma 3, and Qwen 2.572b.
Wait, did the engineer's Python patches still work on a 70 billion parameter Llama model?
They didn't just work. The learned editing policy improved the average success rate by 7.06 percentage points across those 20 unseen targets.
Are you kidding?
And it achieved that gain without a single step of per-target retuning.
That is incredible. That proves the engineer isn't just memorizing Qwen's mistakes. It is learning generalizable principles of runtime management.
Right.
It learns how to write a generic state tracking algorithm, or like a universal guardrail for tool use that applies whether the underlying engine is Llama, Gemma, or Qwen.
Exactly. And they pushed this concept even further with an experiment they call Agent SFT.
What's Agent SFT?
It explores how the harness interacts with weight updates to the target model itself. So if a team decides to invest the compute to fine-tune the target agent's actual weights on the task data, its baseline success naturally rises.
Right. Sure, because you're improving the engine.
Right. In their test, it went up to 59.2%.
So the engine has been upgraded. Does the transmission still matter at that point?
It matters immensely. When they took that freshly fine-tuned target and applied a target-specific Harness-R1 engineer to it, the score was pushed up to 64.2%.
Wow, so that is an additional 5-point gain on top of the weight fine-tuning.
Exactly.
This is a critical takeaway for your MLOps pipelines. Optimizing your runtime harness does not become obsolete when you train a better foundation model.
Not at all.
They are orthogonal, complementary surfaces for optimization. You can fine-tune your model weights to improve its intrinsic reasoning capabilities and simultaneously train your engineer model to build more robust runtime scaffolds that extract the maximum utility from that specific level of reasoning.
It's beautiful. The engineer and the target can co-evolve.
The harness and the weights are not competing solutions. They're multiplicative.
Exactly.
Okay, we have discussed the architecture and the performance gains. But let's actually look at the Python code this engineer is writing. To understand the mechanics of these patches, the researchers conducted a leave one position out ablation study on those 4 lifecycle hooks.
Yeah, this was a really revealing part of the paper.
If you remove the hooks one by one, what breaks?
So the ablation study reveals that the dominant hook is entirely dependent on the nature of the environment.
Oh, interesting.
Right. For WebShop, which is dominated by immediate, high-stakes actions like clicking buttons or submitting forms, the pre-action mediation hook was the most critical.
That makes sense. You want a firewall before you click buy?
Exactly. If you remove the pre-action hook, performance drops by 3.9 points.
Massive drop.
But conversely, for ALFWorld, which requires long horizon planning and the ability to recover from physical dead ends in a simulated room, the post-feedback recovery hook is the most vital. Removing it costs 3.3 points.
To make this concrete, let's look at a specific case study from WebShop. There is a classic LLM failure mode known as the premature purchase.
Oh, I've seen this ruin so many autonomous shopper bots.
It's so common. Imagine your agent is tasked with navigating an e-commerce site to buy a synthetic hairpiece,
Yep.
and the instructions strictly specify it must be the color black-brown.
Okay.
The unpatched agent successfully searches for the item, it navigates to the correct product page, sees the Buy Now button, and it just clicks it immediately.
Without selecting the color.
Right. It completely forgets to select the color from the drop-down menu first, and it fails the task.
It is a standard alignment failure, where the model prioritizes reaching the terminal state over fulfilling the necessary prerequisites.
So the Harness-R1 engineer receives this failure trajectory. It analyzes the sequence and writes a JSON patch that injects a pre-action guardrail.
This is where the magic happens.
Right. This Python snippet intercepts any Buy Now action before it is sent to the web environment. The code actively checks a runtime predicate. Are there required options on this page that are currently unselected?
Simple but effective logic.
Very. If that evaluates to true, the Python code explicitly blocks the Buy Now action and forces the target model to receive an injected prompt saying, you must select the required options before purchasing.
So it interrupts it?
Yes. The model reads the prompt, realizes its omission, selects the black-brown color, and then executes the purchase. It turns a guaranteed failure into a success using just a few lines of conditional logic acting as a firewall.
And that targeted intervention is exactly why Harness-R1 succeeds where frontier models fail.
Right. Let's look at the contrast.
Let's look at how Gemini 3.5 Flash handled a failure in ALFWorld. Gemini analyzed failure traces and noticed the agent was struggling with object placement. So it wrote a pre-action hook that aggressively forced the agent to place objects based on a faulty internal stage estimate.
Okay, why was that bad?
Because ALFWorld features complex 2-object tasks, where you have to collect both a sponge and a soap before placing them in a sink.
Oh, no.
Yeah. Gemini's rigid patch forced the agent to place the first object immediately upon finding it, completely destroying the agent's ability to complete any 2-object tasks in the entire environment.
Because Gemini was just guessing at what plausible code looked like. If Harness-R1 had generated that same overly aggressive patch, it would have run the GRPO loop.
Exactly.
It would have tested that patch across a batch of tasks, seen the catastrophic drop in the same batch success for 2-object tasks, assigned that specific token sequence a heavy negative advantage, and updated its gradients to avoid writing that kind of logic in the future.
The RL loop enforces a strict discipline of empirical utility.
It grounds the code generation in the actual mechanics of the environment, not just human aesthetics.
Precisely.
So to summarize what this means for your own agent deployments, Harness-R1 proves that agent harnesses should no longer be static, manually engineered Python files.
Throw away the static wrappers.
They shouldn't rely on generic prompting templates that apply the same heuristic to every problem either. The runtime environment surrounding an LLM can, and frankly should, be dynamically coded and continuously optimized by a dedicated RL-trained engineer model that actually learns from the real-world failures of the system it is managing.
It is a fundamental shift from human-engineered scaffolds to AI-engineered, empirically validated execution environments.
I want to leave you with a final implication to consider for the future of your AI infrastructure.
Oh, this is the part that keeps me up at night.
Right. This paper tested a single adaptation step going from a vanilla target to a fine-tuned target and generating a static engineer model for it. But imagine automating a continuous multi-round loop of this process.
Just letting it run.
Picture a deployment where your target model updates its core weights via online learning overnight, and the harness engineer simultaneously analyzes the new failure logs to dynamically update the runtime code by morning.
A completely autonomous feedback loop.
You create an infinite loop of compounding, self-directed AI improvement where the engine and the pit crew optimize each other continuously. How long until that harness engineer is writing complex middleware, multi-agent mediation protocols, and dynamic state tracking algorithms that we, as human engineers, can no longer fully comprehend?
It really suggests we are rapidly approaching an era where AI doesn't just write the application code. It actively architects the fundamental execution environment it resides in.
Consider what that means for your current MLOps stack. Thanks for joining us for this deep dive on AI Paper Slot.